work out this hybridization. The first one is sp hybridization, which will involve the s orbital, a single s orbital, and the single p orbital, of course with same principal quantum number. Let's take an example of beryllium chloride molecule. It is a covalent molecule because the electronegativity difference between beryllium, though it is a metal, and chlorine is less than 1.9. The central atom is beryllium and the surrounding atoms are chlorine. The ground state valence shell configuration of beryllium is in fact having 4 electrons, so it is 1s2, 2s2. So we will only consider the valence shell, that is 2s2 and 2p vacant orbital or 2p0. So this is the orbital diagram. There is nothing in 2p. And in this beryllium has no unpaired electrons. So it's obvious if there is no unpaired electron, then why should it form the covalent bond? The covalent bond is formed actually when the overlapping of atomic orbitals with single occupied electrons are taking place, but it is having a paired orbital only and other orbitals are vacant. So how to explain the formation of this beryllium chloride molecule? A simple technique is check the number of surrounding atoms or how many bonds it is going to form. Since it is going to form 2 covalent bonds, it's obvious that it needs 2 half-filled orbitals or 2 single occupied orbitals. In order to explain so, let's see the valence shell configuration. Of beryllium in excited state, that is the state with slightly more energy than that of ground state. This will be 2s1 and 2p1. One of the s electron would migrate to the adjacent p orbital. Now these 2 orbitals will undergo hybridization, and this hybridization will now be known as sp hybridization. As a result of mixing of these 2, we will get 2 hybrid orbitals, each named as sp, and other 2 pure 2p orbitals would remain over here. Since 2 electrons are there, so single electrons will occupy over here as per the Hund's rule. Then let's come to the formation of covalent bond with 2 Cl atoms. So this is our beryllium, the central atom with single electron, sp. This is also sp. This is just for beryllium, and the 2p vacant spaces are there. Though electrons are not there, but the vacant space we need to write. A pure covalent bond, then the second electron will be provided by another chlorine. And this is the beryllium. This is our sp orbital, maximum possible apart, that is at 180, and this is the Cl. Its pz pure orbital will overlap to form the bond pair. The 2 electrons would be here, and the shape of the molecule will be, we will only see the sigma bond. It is along a line. This is also along a line. The bond angle is 180. So the shape will be linear with bond angle 180 degree. That's how this is being formed. Now here I'll explain one particular point. How that excited state is being formed. You consider this as the central atom or beryllium atom. This one is the beryllium atom. It has a configuration ground state 2s2. The two chlorine are approaching this beryllium. The two chlorine are approaching beryllium. This is one chlorine and this is another chlorine. These two chlorine are approaching beryllium. So what will happen to this beryllium? These two electrons are being faced by the 3p half-filled electron of chlorine. This also 3p half-filled electron of chlorine. Since this 2s electrons are being experiencing an electron-electron repulsion by the presence of nearby chlorine electrons, so a slight lift in potential energy would take place and it goes to the excited state. This excited state energy is enough to shift the 2s electron to 2p, right? So hope so this part is being clear. Let's see another example, that is our Sp2 hybridization. In Sp2 hybridization, Sp2 hybridization will take the example of BF3 molecule, boron trifluoride, or we can take BH3 or we can take AlCl3, and we have explained this all as electron deficient or electrophiles. Boron with 5 electron has configuration of 1s2, 2s2, 2p1. So now the same thing, ground state valence shell configuration of boron is 2s2, 2p1. The orbital diagram is like this. Since it has to form 3 covalent bonds, it requires 3 half-filled orbitals, but practically we are having how many half-filled orbitals? 1 in ground state. So again in excited state configuration, excited state valence shell configuration of boron would be 2s1, one of the 2s would migrate over 2p, 2p2. So one is 2s1, another would be 2p2. Done? If this is so, now we have the 3 orbitals with single occupancy. These 3 orbitals will undergo hybridization, and since 1s and 2p orbitals are there, this is Sp2 hybridization of boron. And how many such orbitals would be there? Number of pure orbital is equal to number of hybrid orbital. Each one will be named as Sp2, and the filling up of electrons will be as per Hund's rule. So 1, 2 and 3, this is as a whole the boron, and the other 2, this other 1, 2p orbital will remain vacant over here. This is of course with different energy. Finally, coming to bond formation of boron with any one we could take with 3 hydrogens. Suppose each hydrogen is having s orbital, and there is no problem in orientation because all 3 sp2 orbitals will have same orientation. So this is forming, there is no problem in internuclear axis. This is also sp2, sp2 and sp2 with single occupancy of boron, and with hydrogen it is forming, this is the 3 hydrogen, 3 electrons provided by 3 hydrogen. the shape of the molecule will be, here is the molecule, this is the central atom boron, this is one fluorine, this is another fluorine, this is another fluorine. This is the bonds making a bond angle 120, just the blades of the fan, and this is an imaginary line joined to get the full shape of the molecule. Yes, it is trigonal planar with bond angle 120, considering the lobe of the fan as the central atom and the three end of the blades are of the fan are the three fluorine or three, here I have taken hydrogen. In fact, if it is fluorine, we could have taken this 3f, and instead of s orbital it will be the pz orbital. So this is how BH3 is being formed. The shape is planar, trigonal, and the bond angle is 120 degree. Now see, if we have two orbitals to be placed, so best way is 180 degree. If three orbitals are supposed to be placed here, then it must be like this, the blades of the fan. This is the maximum possible distance, 120, 120, 120. This is how the orbitals are actually being arranged. Okay, so up till Sp2 is there. Next onwards we will see Sp3, then the involvement of d orbitals and more complicated shapes, and then next onwards the three-dimensional shapes also.